Okay. So hello everyone. Welcome to the week 13 of the problem solving session for the discrete maths course. And today what we'll do is we'll summarize the topics that we have seen throughout the course. And we may not be able to cover all of them, but we'll try to look at some examples, some important concepts, and try to recall them through examples. Okay. So let's start with some simple things that we saw in the beginning. So first things that we saw was some counting techniques. We saw that okay, yeah. So okay, so for example, we saw that if you have to choose two different okay, so let's say you have some 10 blue balls and some 5 red balls, and you are asked to you're asked to find the number of ways in which you can choose 2 blue balls and 3 red balls. Then what you do is you independently find out how out of 10 blue balls in how many ways can you choose two blue balls. So that turns out to be 10 choose 2. And also recall that this is 10 choose 2 and not 10 not 10p2, because in this case the order does not matter, because all the blue 10 blue balls are identical, so it does not matter what order you pick them, in what order you pick them. And yeah, and similarly for the red balls you have 5 choose 3 ways. And then the question is, what do you do with these two quantities? Do you add them or do you multiply them, and so on? And the answer to that is lies here in the keyword, that you're independently choosing these two events, and since there is an and as a keyword, you'll always end up multiplying them. So this is what is called the rule of product. And yeah, so so that is a quick recall of the rules and the combinations and permutations that we saw. And we also saw one technique called stars and bars counting. So what does that say? If you have n stars and you want to place r bars amongst them, so the bars could be anywhere, so but you want to place r bars so that they form r minus 1 bars, so that they form r partitions. So notice that if you have one bar then you are basically partitioning your set into two. So in order to make r partitions, you will need r minus 1 bars. So the number of ways of doing this is what is given by n plus r minus 1 choose n, and this is what we call the stars and bars counting. And yeah, so the way to see this is also not very difficult. The idea is that you think of your you think of this string as an n plus r minus 1 length string. So here you have n plus r minus 1 many spaces, and what you're going to do is you're going to either fill them with a star or a bar and star or bar and so on. So there are precisely n stars that are going to be there, and there are precisely r minus 1 bars that are going to be there. So this is same as n plus r minus 1 choose n, which is same as n plus r minus 1 choose r minus 1. And this is how we derived at this expression, which becomes very handy when we try to solve the word problems. So yeah, so I hope I hope that was enough of a recall. So given that, we'll try to solve this question. So what you're given is you have 12 identical candies that you want to distribute among 4 children, and so there is no constraint on the number of candies that one child can get. It is possible that one child gets all the 12 candies and the rest of them don't get anything, or it's possible that everybody gets something. So there are no constraints like that. So the question that we're asking is, in how many ways can you do this? So so what we'll do is we will think of these, we'll appeal to the stars and bars counting method. So we have this 12 candies, and I'm going to draw them as stars. So you have 12 candies, and you're going to place some partitions here. So this partition tells you the number of candies the child 1 gets. Then this partition tells you the number of candies child 2 gets. So that is so what this means is that the first child gets one candy here, the second child gets none, and then let's say I draw another bar here. So that means the third child gets the third child gets 11 candies, and the third child gets 9 candies, and the fourth child gets 2 candies. So this is one possible distribution. So the question is, in how many ways can I draw this 3 bars into 12 stars? So we know that the answer to that is given by n plus r minus 1, choose n, which is same as 12 plus 4 minus 1, choose 12, which is same as 15, choose 12, and this is nothing but 15, choose 3. This is because recall that this is because of the identity that n choose r is same as n choose r n minus r. And and what is 15 choose 3? That is 15 into 14 into 13 by 3 into 2, and that turns out to be 35 into 13. So this is the number of ways in which you can distribute 12 candies to 4 children where there are no constraints. So this is the answer to the part 1. Now let's say I additionally put in some constraint, and the constraint that we're putting is that each child must now get at least one candy. So what we did here was one example that is not allowed in now. So in this case, the second child does not get anything. So we do not want this in such kind of cases to happen now. So we only want to count those distributions where every child ends up getting at least one candy. So how do we modify the same strategy to so that it works out for the new case? So what you do is you do a really simple thing. So you have 3 children, and what you do is you give them one candy each. So the first child gets a candy, second child gets a candy, and notice that these are identical, so it does not matter the order or anything. So you just give one candy to all of them. So how many candies are we left with? So what you do is distribute one candy per child a priori. And now what happens is, you had 12 candies and we have distributed 4 of them, so you are now left with 8 candies. And now I want to distribute them to the 4 children, but it does not matter how we distribute them. So it now amongst these 8 candies, it's possible that all the 8 candies go to the third child, and none of the other child gets anything, or it's possible that all of them get 2 candies each, or anything. So it does not matter that some child does not get anything out of these 8 candies, because we have already ensured that each child has already gotten their quota. So this is same as saying that you have 8 stars. Okay, the same as saying that you have 8 stars and you're going to put 3 bars into them, and that is same as saying that n is 8, r is 4, and the number of ways of distributing that is nothing but n plus r minus 1, choose r minus 1, and this is nothing but 11, choose 3, and this is nothing but 11 into 10 into 9 over 3 into 2, and this turns out to be 15 into 11, which is 165. So the number of ways in which you can distribute the candies now such that you're guaranteed that every child gets something is 165. Okay, so that does a basic revision of the basic counting ideas that we studied earlier. And Now let's look at some propositional statements that we've come across. So what is a proposition? A proposition is simply, so maybe I'll just call this basic counting. Okay, so what is a proposition? Proposition is simply a statement, and what does the statement do? The statement is either a true statement or it is a false statement. So it can either take a value of true or it can take a value false, but it cannot be something in the middle. At any point of time it has to take one of the two values. It can't be anything in between. So for example, let's understand this with the example that is given here. So here you've been given statement. So what is the statement? I'll underline the statements. So the statement is I am sick. So maybe I'll call it S, and S is the statement that says I am sick. So at any given point of time, either I am sick or I am not sick. It cannot be that I'm somewhere in between. Okay, so this is what the statements are. The second statement is that there will be no lecture today. So I'll call it L. The second statement is there will be no lecture today. And let me write down all the statements here, all the propositions here. So okay, maybe I'll not negate it in the first place. I'll say there will be a lecture today. So that if I want to say that there will be no lecture today, what I'll do is I'll simply write it as negational, and that will do the job. So just to be consistent, there is no hard and fast constraint that proposition needs to be positive, but in this case it just makes the job easier to think about intuitively. That's why I'm making it positive. I'm making the statement to be positive. When I want to use it in the negative sense, I'll use the negation. So yeah, so the third statement here is students are happy. So I'll say H is the proposition that students are happy. And that's it. So we have three propositions here, and what we do is that okay, so first thing is, notice that each of the proposition here either takes a value of true or false. It cannot be both or it cannot be neither. So that is what the propositions are. Now the question is, how do I write these statements in terms of propositions? So to do that, I'll need something called connectives. How does one proposition relate to the other? So for that we use connectives, and these are called logical connectives, and these could be either and, or that is a conjunction like that. So when I say P and Q, it means P should be true as well as Q should be true. Only then this proposition will take a value of truth. Or it could be connected by an or it could be connected by a negation, or it could be connected by an implication. So what does implication mean? Implication means if P, then Q, and we can write it as P implies Q, and that is same as negation P or Q. This is something we know that these two are equivalent. How do we know that? One thing you can do is you can try to write the truth table for the same. So what you do is you write PQ, and then you write all possible values that PQ can take, and for each of the setting you find out what P implies Q takes, the value of P implies Q and the value of negation P or Q. And one thing that you should ensure is the value of both the entities should be the same at every row. So if this is 0, this must be 0. If this is 1, this must be 1, and so on. So if the truth tables of both the statements are matching, then you will say that you will conclude that they are equivalent. So this is just one way of showing that two logical statements are equivalent, we also saw some rules of inferences that will make your life easier to show that two statements are equivalent. So I'll not get into the details of it, but I just want to I just want to quickly recall. And another way, one is the truth table method and the other is the rules of inferences. So I'll just leave it at that. So I just wanted to bring it to just refresh the concepts by recalling it. Okay, so these are the logical connectives, and what we will do now is for each of the statement that is given to us, we will write them in the using the logical connectives. So the first statement is that I am sick. If I am sick, there will be no class today. What does that mean? That means if I am sick, then there will be no class. That is negation L. So that there will be no lecture. So this is nothing but P implies negation Q. And what is the other statement? It says either there is a lecture today or the students are happy. So this or here is a keyword that tells us that the connective that we are using is a logical or. And what is the statement? This is that either there will be a lecture today, so that is L, or the students are happy, that is H. And the third statement that we have is that the students are not happy. So what does that mean? It is negation of H. So I'll copy these statements to the next page. Okay, so now what we know is that now what we know is either L should be true or H should be true. Okay, but if H is not true, that is, this is if H is not true, then it better be the case that L is true, because if L is also false and H is also false, then this statement cannot be true. So therefore this is the conclusion. Okay, so this is the conclusion that follows from the two statements. Now what we know further is S implies negation L, and we know that this is equivalent to negation S or negation L. And again, from here we know that either negation S should be true or negation L should be true. Okay, and if L is true, then this implies that negation L is false. Therefore we know that either negation S should be true or negation L should be true. But now we know that this is not the case, therefore it should better be the case that negation S is true. So what is the logical conclusion of this? The logical conclusion is negation S. And what does that mean? S is that I am not sick. Sorry, I am sick. Yeah. S is that I am not sick. Therefore negation S will be that I am not sick. And this is the valid conclusion that follows from the three statements that were given to us. So just to quickly recall, what we did is, given these statements, we first identified the propositions that are there, and then using the connectives that are there in the English statements, we converted it into the propositional logic by using the connectives. And now given these, we are trying to use the rules of inferences to derive conclusions. So for example, first we only look at these two statements. So this is what we have written. This says that either L should be true or H should be true in order for the statement to be true. But now we know additionally that H is not true, therefore it has to be that L is true. So this is what we conclude from the two statements here. Next we look at this proposition here. So this is S implies negation L. Using the equivalence, we know that this is same as negation S or negation L. So this says that either negation S is true or negation L is true. But now we know additionally that L is true, therefore negation L is false, therefore it should be that negation S is true. And this is what it means. It means I am not sick. And yeah, so okay, so the answer for this is B. Okay, so that is a quick recap of propositional logic. And so given that, we will move on to the next concept of relations. So okay, so um, yeah, so what we know is that a relation is nothing but a subset uh, of direct product of sets. So for example, I have a set S which is 1 2 3 4. And what is S cross S? S cross S is the direct product of the set S with itself. So this will look like 1 comma 1 1 comma 2 1 comma 3 1 comma 4 2 1 2 2 and so on to 4, and finally 4 1 and so on up to 4 4. So this is nothing but entry wise element by element product of the set. And if I want to write S cross S cross S, for example, then this becomes a 3 tuple. So what you have is 1 1 1 1 1 2 and so on 1 1 4. Then you have 1 2 1 and so on up to 1 2 4 and so on. So basically, how many entries would be there if there are 4 elements in the set? Then the size of S cross S cross S would be 4 into 4 into 4, which is 4 cube. So in this case, S cross S has a size of 16. Okay, so let us recall what is a relation. So a relation is any subset of direct product of sets. So for example, I can choose this element, this element, this element, and this element to be in my relation. So for example, one valid relation would be 1 comma 1 3 comma 1 3 comma 4 and 4 comma 4. So to simply put it, relation is essentially just a subset of direct product of sets. And there are different representations that would graphically capture relations. So for example, one way to okay, one way to represent relation is very obvious, that is the matrix formulation. So what you do is, on one hand you write the elements of the set S, and on the column side also you write the elements of the set S. Now this entry here tells you whether the element is related or not. So 1 comma 1 is in this set, therefore I'll write a 1 here. But 1 comma 2 is not, therefore I write a 0, and so on. So the only entries that get 1 are 3 comma 1 3 comma 4 and 4 comma 4. So you have 3 comma 1 3 comma 4 and 4 comma 4, and everything else is a 0. So this is one possible representation of a relation. And yeah, and the other possibility is that you write it graphically. So the second representation would be you write a graphical representation. So what does that mean? The elements of the set S are the nodes here. So in this case there are 1 2 3 and 4. So in this case there are 4 nodes that you have, And what do I do? I draw edges whenever two elements are related. So in this case, the relation is 1 comma 1, 3 comma 1, 3 comma 4, and 4 comma 4. So what I do is, I know that 1 comma 1 is related, so I draw an edge from 1 to 1. I know 3 comma 1 is related, so I'll draw a directed edge from 3 to 1. I draw 3 4, therefore 3 to 4, and 4 comma 4, so 4 to 4. So notice that it is important that the edges here are directed, because if I don't draw the direction, I would not be able to differentiate between whether 1 is related to 3 or 3 is related to 1. So if the edge were not directed, I can't tell whether it is 1 3 or is it 3 1, which are two different things. Therefore it is important that the graph is directed. Okay, so yeah, so this is what the graphical representation roughly is. And so okay, so that was just to quickly recall the concepts. Now that we have this in our mind, let us formulate this question in terms of a relation. So okay, so recall that if I give you a graph, then a directed walk on that graph would be simply a list of vertices, edges, and so on. So for example, I'll take an example here. So let me just draw another graph. So what is a directed walk? So let's say you have this. Okay, so let's say I have this directed graph G or D, and when I say a directed walk, what I mean is I'll start at some vertex. So let's say I start at 5. So I first write the vertex name, then I'll take an edge, there could be multiple. I'll just randomly take one, and maybe I'll call these edges as maybe. Okay, so maybe I'll call this edge A, B, C, D, E. Okay, and then let's say I take the edge yeah, so I'll do it again. So let's say I start at the vertex 5. So I'll write the vertex 5 here. Next, I'll write the name of the edge that I'm going to take. So let's say I take edge A, then I'll write that edge. So after taking that edge, I have landed up in the vertex 1. So I'll write the name of that vertex. From this vertex 1, I can take any of the outgoing edges. In this case, I'm, let's say, taking C. So then I'll write the name of the edge, which is C. After taking C, I have landed up in the vertex 4. So I'll write the vertex 4 here. And from this vertex 4, let's say I'm taking this edge T, and I land up at the vertex 2. So I write 2 here. So this is a directed walk. This is a directed walk. What does that mean? I'm essentially starting at a vertex, then I take some directed edge, then from that vertex I take another directed edge, from the new vertex I take another directed edge, and so on. So this is what a directed walk would look like. It will be a sequence of vertex, edge, and so on. So now let us define a relation. So let me define a relation on the R is a subset of V cross V, where V is the set of vertices in this graph, and which in this case is 1, 2, 3 up to 5. Okay, so what I'll do is I'll say that two vertices are related, that is U, V are related if there is a directed walk from U to R. So from U to V. So in this case, for example, the vertex, if you start at the vertex 5, you have a directed walk that can take you to the vertex 2 by taking these edges. So therefore 5 comma 2 would be in this relation. But for example 5 comma 4 cannot be in this relation, because there is no set of edges that you can traverse starting at 5, sorry, not 5 comma 4, I mean 4 comma 5. Okay, 4 comma 5, because there is no set of edges that you can start from 5 and go back to 4, and start at 4 and go back to 5. Therefore 4 comma 5 would not be in the relation. So that's how we have defined the relation. So two elements are related if from the first vertex you can take a directed walk and reach to the second vertex. That's how we define the relation. Now the question that we're asking is, what are the properties of these relations? So notice that we had defined some properties. Given any relation, you can define properties associated with it. So those are reflexive, symmetry, antisymmetry, and transitivity. So let's check one by one whether the relation that we have defined satisfies these properties or not. So what do we mean by reflexive? Reflexive means that every element A, for all A in the set S, A should be relative to A. So in this case, what would that mean? It would mean that from a vertex U to U itself, do you have a directed path, which is true in this case, because what you do is you start at 1, you don't take any edge, or and you go and you're still at 1. So this is starting at the same vertex, you can always reach to the same vertex by not taking any edges. So therefore this relation is reflexive. And what about symmetry? Symmetry says that for all elements A, B in set S, A not equal to B, A, B is related, implies if and only if B, A is related. What does that mean? In our case, according to the relation that we define, what this means is, if you have a directed walk from vertex A to B, you should also have a directed walk from vertex B to A. So is that true? So in this case, for example, you have a directed walk from 5 to 4, which is you take the edge A, you go to the vertex 1, then you take the edge C and go to the vertex 4. So there is a directed walk from 5 to 4, but there is no directed walk from 4 to 5. So this vertex is not reachable. So therefore this is not symmetric. So this is not symmetric because you can have 5 to 4, there is a directed path, directed walk, which is start at 4, go to A, you reach to 1, then take C and you reach to 4. But 4 to 5, there is no directed walk. Okay, and let us look at antisymmetry. What does antisymmetry say? Antisymmetry says that AB is related, implies BA is not related unless A is equal to B. So if AB are two distinct elements, then either AB is related or BA is related. So notice that this need not happen, because for example, let's look at this example. If you look at the vertex 1 and the vertex 3, there is no directed walk that will ever take you to the vertex 3. So 1 comma 3 is not in the relation. But let's ask whether 3 comma, okay, maybe maybe this is not a very good example. Okay, not 1 comma 3, maybe 5 comma 3. So I'll take 5 comma 3 as our example, sorry. So let's say 5 comma 3. If I start at 5, there is no way that I'll ever reach to 3. So no matter what edges I take. So 5 comma 3 is not in the relation. Now let's ask whether 3 comma 5 is in the relation. So let's say I start at 3 and I take this path. I can never reach the vertex 5. So 3 comma 5 is also not in the relation. So this contradicts the property of antisymmetry, that which says that given any two elements, either AB is related or BA is related, which is both not true in this case. We have an example where AB is also not related and BA is also not related. So then you know that this is not antisymmetric, because the example is 5 3 is not related in the example and 3 5 is not related. So whenever you want to say that certain property is not true, what you do is you give a counter example. You come up with a graph and two vertices in this case which do not satisfy the property. And let's ask the interesting one, which is transitivity. What does transitivity say? It says that for all A, B, C elements, AB is related, BC is related, implies AC is related. So what does that mean in this case? It means that it simply means that if you have AB is related, then if you start at A, there is some directed walk that you can take which will take you to B. And what does BC mean? BC is related means if you start at B, there is some directed walk that you can take that will take you to C. And now notice that this already gives you a directed walk from A to C, because what you'll do is starting at A, you take this path, from B you take this path further. So this gives you a directed walk from A to C, and therefore AB is related and BC is related implies that AC is related. And notice that you need not worry about some vertices or edges repeating here, because by definition a walk is something that allows you to repeat the edges or repeat the vertices. So by definition there is nothing that you need to take care of. If it were a path, then that's a different question. We will not get into it now, but in this case it's a walk, so it directly follows. So this is fine, because walk allows repeated vertices and edges, therefore this directly follows. And okay, so that was a quick recap about what relations are and how do we represent them and what are its properties. And notice that we also saw that if a certain relation satisfies reflexivity, symmetry, as well as transitivity, then all three of them, then it's called an equivalence relation. And if a relation is an equivalence relation, it will partition the set of all elements into what are called equivalence classes. So if this is the set of all the elements that you have, and R acts on this set, then it will partition your set into equivalence classes like that. So and maybe we will not get into the details of this, but I'm just quickly just quickly bringing it up. And there are certain properties, some interesting properties of these equivalence classes, their sizes and the number of equivalence classes and so on, but we will not get into the details of it because we want to recall the other concepts that were there in the course. So yeah, so I'll move on to the next question, which is called the principle of inclusion exclusion. exclusion. And what we will also do is we will also recall what are called functions and their properties. Okay, so what are functions? So to quickly recall, what are functions? Functions are special kind of relations. So where what you know is that relation is can be thought of, you have two elements, you have yeah you have sorry you have some two sets here, some set A and some set B, and what this tells you is whether this element is related to this and so on. So you can think of these as edges. And what does a function do? A function simply says that if I'm standing at some vertex, some point in set A here, I cannot basically go to two elements like that. So if I'm here, I can go to at most one of them. So it's not possible that f of a is equal to b, and say f of a is also equal to some c here. That is not possible. So that is essentially what it means. If I give you one element here, I can only go to one element, from at most one element from the other set. And now that we have this, there are different kinds, different properties that we observe about the function. So one are what are called onto functions, and the other is what is called one function. So what is an onto function? What is an onto function? You have, say, some elements here. Let's say you have element 1 here, it goes to A, and 2 which goes to B, and 3 which goes to A. So notice that this is allowed. There can be two elements that go to the same the same element, but that is allowed, but it can't be that, say, one goes to A as well as B. So this is some subtle difference in the definition. And let's say now there is some C which is unmapped, and then there is some D which is also completely unmapped. So this is, so if such a thing exists, then the function is not onto. So you cannot have some elements here which do not have an image in this set. So if such elements are not there, that is, if all the elements in the set B are covered, by covered we mean that for all x in B, there exists a y in A such that f of y is equal to x, then the function is onto. So basically, in simple terms, there should not be some elements here that do not have a pre-image. This is what we mean by onto. And what does 1 mean? So 1 is simply that you have a set here, you have a set here, and and you have some element 1 here, it goes to A, some element 2 here, it goes to B, C, and D, let's say. Now let's say I add one more vertex here, and 4 also goes to C. Then this function is not onto, because what onto says is, if I look at any element in this set B, let's say I look at A, it should have only one pre-image. If I look at B, it should have only one pre-image, one or none. And if I look at C, for example, then I should have only one pre-image. But if I look but if I add this edge, then the property is violated, because now C has two pre-images, one goes to 3 and one goes to 4. So what 1 says is, if I look at some element in the set B here, I should have at most one pre-image. I should not have more than one pre-images. So if I have to write it formally, what I'll say is, for all x in the set B, there cannot exist y not equal to z, such that f of y is also x and f of z is also x. This should not happen. So then if this property is respected, then we'll say that the function is 1. Okay, so This is the formal definition, and the simple intuitive definition to keep in mind is, if I look at any element here, there should be at most one edge going out. Okay, so given that, quick recall of functions, what we will do is, we want to count the total number of functions that are not onto. So to do that, what we will do is, we will break our example um, into smaller chunks. So first what we will do is, I'll not worry about the function being onto or one or anything. What I'll say is, I'll just count the total number of functions. So you have a set A, and you have a set B, and there are, say, n elements here, and there are m elements here, and I want to find the total number of functions that are there. So what you will do is, for the first element here, there are m choices. It can go to any of them. So for the first element 1, there are m choices, like that. So it can go to any one of them. For the second element here, again there are m choices, because I'm just counting the total number of functions. So it could also go to any one of them. So that is also m. For the third element also we have m choices, and so on. So for all the n elements there are m choices independently, and we are simply interested in the total number of functions. So the total number of choices for 1 and total number of choices for 2, and so on. So therefore what we'll do is, we will apply the rule of product here, and that tells you that, so we will apply the rule of product, and that tells you that you should be multiplying all these quantities. So the total number of functions would be m into m into m, and so on. And how many elements are there? There are n elements, so this would be m to the n. And yeah, so okay, so maybe I think I switched between n and m here, that's why you are getting this answer. So maybe I'll, just to be consistent, I'll make this n, and I'll make this m, sorry, m and n, and so that changes the other answers as well. So okay, I'm just replacing m with n. So you have n into n into n into n, m times, so that gives you n to the m. And that answers the first question, which is, we are just counting the total number of functions. Now it's possible that some of them are onto and some of them are not onto. So I want to find the total number of functions that are onto. So eventually I want to eventually that is what I want to find. So what I'll do is, I'll use what is called the principle of inclusion exclusion. And what does it say? So okay, so this is called principle of inclusion exclusion. And what does that say? So I'll before writing the entire principle, I'll recall where did this concept come from, because if I just write the formula, it will be a bit scary maybe. So I'll recall with the simple concept that we had done earlier. So let's say you have this set A, you have this set B, and this is this part here is the intersection of this is the A intersection B, and this part here, this is the union of A and B. And now let's say I want to find out, if I want to find out what is the value of A union B, okay, then we know that this is same as A union okay, maybe okay, if I want to find the value of A union B, then what I do is I first find the value of A, that is this entire set. Then I find the size of the other set, which is this part B. But what happened in the process is that the elements that were common to both A and B got added twice. But I only want to add them once. So what I'll do is I'll subtract it from the sum, so that what I get is I get this part plus this part and this part exactly once, because this was added once here and subtracted once here, so that this part only got added once in the total sum. So this is what this is what we know for two sets. But let's say I have three sets. So I have A, B and C. Okay, so let's say I have three sets. This is A, this is B and this is C, and I want to find the value of the union of all of them. That is, I want to find out this entire A. So I want to find A union B union C. Okay, so now what we do is I'll simply add the three quantities, which is size of A plus size of B plus size of C. And what does that give you? It adds, so you're adding this quantity and adding this quantity. But what happened in this process? What happened is that this part here, which is A intersection B, got added twice, like it happened earlier. It happened in the previous example also. So but I don't want to add it twice, I only want to count it once. So what I'll do is I'll subtract it once. So I'll subtract A intersection B. But wait, the same thing happens for A intersection C as well. It's a symmetric case. This part got added once in A, it got added once in C. So it got added twice. So I'll subtract that once. And similarly, the same thing happens for B intersection C. So I'll subtract that once. But now what happens is this small part here, the small shaded part here, let's count how many times it got added. So it got added once for A. So maybe I'll write this down. So it got added once for A. It got added once for B also, because it is also in B. And it got added for C also. Okay, so it got added thrice, but we also subtracted some terms. So what happened to this count? So we subtracted this, and therefore this part also got subtracted for A intersection B. When we subtracted A intersection B, again this part got subtracted. When we subtracted for B intersection C, again this part got subtracted. So we added this thrice, and then we subtracted it three times. Once for A intersection B, once for B intersection C, and once for A intersection C. So this we subtracted three times. So essentially we did not add it at all. We added thrice, we subtracted thrice. But in this entire union, this part never got added. So what I'll do is I'll simply add it into the set. This is nothing but A intersection B intersection C. So this is what you get for three sets. For the two sets it was a bit simpler. For three sets it's a bit complicated, because the number of intersections that you keep on getting is getting more and more complicated. So if I give you 4 sets, 5 sets or 40 sets, it becomes very difficult to keep track of all these intersections and all possible subsets, and whether to add, whether to subtract, and so on. So what we do is we write a very very succinct a formula for finding union of k sets, and this is given by the principle of inclusion exclusion. And how do we write that? So if I want to find, you have say A1, A2 and so on up to AK sets, then the union of maybe I'll write it this way. So then A1 union A2 and so on up to AK, this is given by the summation of you look at all possible subsets of, let's say n is the, um, or let's say, maybe I'll call this n. You look at all possible subsets, and what you do um, is that you find the value of ai for it. And what do I mean by ai? Ai is simply, let's say, maybe I'll show it with an example. So let's say I is a subset of n, right? So let's say I is 1, 3 and 5. Then how do I define ai? Ai is nothing but a1 intersection a2 a3 intersection a5. So in general, ai is nothing but is nothing but intersection of ais for I in I. And notice that this is basically taking care of the fact that whether I should be whether I should be looking at a single set, or whether I should be looking at two intersections, or whether I should be looking at three intersections, and more complex. And the minus sign here tells you tells you whether you should be adding the quantity or subtracting the quantity. Because notice that if the size of the set is odd, then you're adding the quantity. So if I is 1, for example, then you should be adding. Therefore this minus 1 to the 1 plus 1 becomes a 1, so you will end up adding. But if this quantity is even, there are two sets that are intersecting, then you should be subtracting. And this sign, this will basically appropriately take care of the fact that whether you should be adding it or whether you should be subtracting it. So this is the nice formula that PIE gives us. And what we will do is we will solve this question of counting the total number of onto functions by using this idea of principle of inclusion exclusion. So okay, so let me start with that. So what I want to do is I want to count the total number of onto functions. Okay, but what I'll do is instead I will what I'll do is maybe I have this universe, which is the total number of total functions that I have. And let's say that a function is not onto. So when do I say that a function is not onto? So it is possible that 1, 2, 3 and so on up to n, and so on up to n. So it is possible that there is a function that goes like this, and it never ever covered this element n. So there is nothing that goes back to this set. So it is possible that this element remained uncovered, and therefore the function is not onto. So a1 kind of tells me that the function is not onto because the element 1 is not covered, and a2 tells me that the element 2 is not covered, a3 tells that element 3 is not covered, and so on. So you have all the way up to an, and all the way up to n, and you have all possible intersections, all the possible complex intersections that are possible. And what I want to find out is, so where are the onto functions? The onto functions are exactly sitting outside these spheres, because AIs represent the functions that are not onto. So let me define AI more formally. So AI is the set of functions from A to B that where element 1 is not covered. So element I is not covered. Okay, and what we want is the total number of onto functions are exactly a1 union a2 and so on up to an unions complement. This is what we want, because this union which is inside the spheres is a bad set, and what I want is what is outside. So I want the complement of this. So this is nothing but size of u minus the size of a1 union a2 union and so on up to an. And what do I know about this? This is the total number of functions from a to b, and this is something that we previously calculated. What is that? This is what we know from the part a, and that is n to the m. So this is n to the m, and what I want now is this quantity a1 up to an. This is what I want to find out, and this is what is given by the principle of inclusion exclusion that we just now wrote. We know that this is given by this quantity, so this is where the PIE comes in, and we know that a1 union a2 and so on up to an is given by summation I subset of n not equals v minus 1 to the size of I plus 1 size of a. And okay, and now what I need to do is, in order to solve this, I want to find out the values of AIs for all the sets. Okay, so what does that mean? So what does that mean? So let's say okay, so let's say that I for me is 1 3 5, like we said earlier. So there are these elements here 1 to m, and then you have 1. Maybe I'll take a simpler example. So I'll say 1 2 3, and then you have 1 2 3, and then you have the rest of the element. So now what does the function do? For every element, it will just take values from the other set, and it will not even touch the elements 1 2 3. So let's count the total number of functions that would be like that. So for the first element, you have n minus 3 choices, because there were n elements here and 3 of them are not to be touched. So for the first element, you have n minus 3 choices. For the second element, you have n minus 3 choices. For the mth element, you have n minus 3 choices. Therefore totally you have n minus 3 to the m choices. If I do not want to cover the numbers 1 2 3, but let's say I is n minus 1 n minus n minus 2 n minus 1, and then let's say this is what I is. Then what happens is I'll not touch the last 3 elements, and I'll just add my arrows like that. So again, let's ask the question, for the first element here, how many choices do I have? For the first element, there are n minus 3 choices. For the second one, there are n minus 3 choices, and for the mth one also, there are n minus 3 choices. So this one also, the number of elements that you end up getting is n minus 3 to the m. So what is the conclusion? What is the observation here? The observation is that it does not matter what 3 elements I am excluding, as long as the size is the same. So whenever so this quantity only depends on the size of the set. So I can write this as, so the summation that we had there was minus 1 to the AI. So I can write this as summation k is from 1 to n minus 1 to the k plus 1 n choose k times size of AI or size of AK, where AK is AK says that I'm excluding the set 1 2 and so on up to k. And so the answer for this AK will be given by, you have n elements here and k of them are not to be touched. So I'm not going to touch this part, but the edges are only going to be drawn like this. So for each of them there are n minus k choices, and this happens m times again. therefore you get n minus k to the m, and plugging this here, what you get is size of union of ai 1 to n is given by summation of k is from 1 to n minus 1 to the k plus 1 n choose k times n minus k to the m. And notice that this n choose k comes in because what we are doing is we observe that it does not matter what elements there are in the set as long as the size is same. So how many sets are there whose size, how many subsets of n can be there whose size is k. So this is precisely given by n choose k. So for all the n choose k, the value is going to be the same. So what we do is we find it for 1 to k and substitute it here, and this is what you get. So this is precisely the expression that we are asked to show. So this is exactly the expression that we wanted to show. And now we want to find, so this is the total number of functions that are not onto, whereas what we were interested in is the total number of functions that are onto. So what we will do is we will subtract this quantity from the total number of functions. So this is the total number of functions that are not onto. So what I'll do is to find total number of onto functions, I'll subtract this quantity from the quantity that we have. This is k is from 1 to n minus 1 to the k plus 1 and choose k n minus k to the m. And notice that suppose k is 0, then what is the value of this expression if k is 0? If k is 0, this is minus 1 to the 1, minus 1 to the 1, n choose 0, n to the m, and this is nothing but minus n to the m. So therefore, and which is negative of what I have here. So therefore what I can do is I can write this as minus of k is from 0 to n minus 1 to the k plus 1 n choose k n minus k to the m. And now what I'll do is I'll pull this minus sign inside here. So what this becomes is, this is summation k is from 0 to n minus 1 to the k n choose k n minus k to the m, and this is the total number of onto functions, and this is exactly what we wanted to show in the first place. So this is exactly the quantity that we end up getting. And yeah, so that is a quick recall of what we did in the functions, the types of functions, their properties, and how to count whether they have this property or how many of them have this property, using this idea of principle of inclusion exclusion. Okay. So now what we will do is we will recall the concepts of recurrence relation. So what is a recurrence relation? A recurrence relation is something that that tells us the the value, how a function grows with respect to its smaller value. So for example, we did this example of tiling where we had an 2 cross n we had a 2 cross n let's say board. We want to fill it with tiles, and we have tiles of this kind, or okay, and tiles of this kind. Okay, and we want to find the total number of ways in which you can tile this, either using, you have infinite supply of both the kinds of tiles. So what we did here is we said that maybe I'll Okay, so this tile can be used as a vertical thing, or it can be used as a horizontal thing, so it does not matter. So what we said is, in order to find the solution for n, by n I mean the total number of columns here, what I could do is I could place this um, yeah, so I could place this one tile here like this and cover these two blocks, and then I can just simply solve it for the 2 cross n minus 1 tile. So this is nothing but n minus t of n minus 1. Or what I could do is, I could cover this 4 blocks, this 4 cells, by putting one square tile here, or by putting these tiles um, horizontally like this, or by putting them side by side vertically like this. So there are three ways in which I can cover these 4 tiles using a combination of these tiles. So there are three ways in which you can do this, and it reduces your problem to a 2 cross n minus 2 board, and therefore it's sufficient to solve it for t of n minus 2. So this is what we call a recurrence relation, where in order to solve for a larger instance, you write it in terms of a solutions of its smaller instance. And given this formulation, it makes the problem really intuitive to understand. And these kind of relations come up very often in computer science when you design algorithms and so on. So for example, this recurrence relation that we've written is precisely what you end up getting in your algorithm for merge sort or for quick sort. It may be a little different, but yeah, this is precisely the recurrence relation that you get for merge sort. And now what you want to do is, you want to solve this recurrence so that you get a closed form relation. So I want to understand how good or bad this is compared to, let's say, n square or n log n or anything. Therefore it's important that you solve the recurrence relation. So there are different methods for doing it, but what we'll do is we will simply do a substitution method for now. So what we will do is solving the recurrence relation. So you have t of n is equal to 2 times t of n by 2 plus n. And what you do is you simply substitute it here. So you get 2 times t of n by 4 plus n by 2 plus n. And if I expand this, you get 2 square t of n over 2 squared plus n plus n. And if I expand this again, what you get is 2 times t of n over 2 cube plus n over 2 square plus n plus n. And this is nothing but 2 cube times t of n over 2 cube plus n plus n plus n. So notice that every time you get an expression like this, and yeah, so this is nothing but 2 to the k times t of n over 2 to the k plus k times n. This is what will end up happening. And now the question is, what should be the value of this k, so that this problem becomes very trivial. That is, t of n over 2 to the k becomes t of 1. That is, n over 2 to the k is equal to 1. Therefore 2 to the k is n, and therefore k is nothing but log n. So if you choose k to be log n, then this problem becomes very trivial. It becomes so trivial that you can just solve it. So let's say t of 1 is 1. Let's assume that. So then what will happen if I substitute k is equal to log n? What do I get here? I get 2 to the log n times t of 1 plus log n times n. And this is nothing but n plus n log n, which is same as order n log n. And that is the solution to the recurrence relation. And yeah, there are different methods for solving this, but in this case it's enough to simply substitute it step by step, and then make it and trivialize the problem, and then um, yeah, then find the solution. So that is a quick recap of what a recurrence relation is. And we also saw that this method may not work always, may not be applicable everywhere. So in general, let's say you have a recurrence relation like this. So you have 13 an minus 1 minus 30 an minus 2. Then what you do is you write this in terms of the characteristic equation. So the characteristic equation here would be x square minus 13x plus 30 is equal to 0. And you find the solutions, find the roots of this quadratic equation. So what are the roots? The roots are given by okay, maybe what I'll do is okay, so the roots are given by b square minus 4ac by 2a, and this is nothing but 169 minus square root 4 okay, maybe maybe what I'll do is yeah, in this case it so happens that you have x minus 3, x minus 10 is equal to 0. So if you expand this, you will get back the previous equation. So it follows that 3 and 10 are the roots for this. So x1 is 3 and x2 is 10. These are the roots of the quadratic equation. And then we know that if these are the, so this is what is called the characteristic equation of the recurrence relation. And then what you do is since these are the roots, we know that the solution for the recurrence relation is given by an is equal to alpha 1 times x1 to the n plus alpha 2 times x2 to the n, and this is nothing but alpha 1 times 3 to the n plus alpha 2 times 10 to the n from the solution that we got for x1 and x2. And now let's use the initial conditions that are given to us. So what we know is, we know that a0 is 4 and a1 is 6. So a0 would be alpha 1 plus alpha 2 and this is equal to 4. a1 would be 3 times alpha 1 plus 10 times alpha 2, this is given as 6. So by solving this, you get 3 alpha 1 plus 3 alpha 2 is 12. So 7 alpha 2 is minus 6, and therefore alpha 2 is minus 6 over 7. So that gives alpha 1 is 4 plus 6 over 7, which is 34 over 7. And if you substitute this finally gives you that an is equal to 34 over 7 times 3 to the n minus 6 over 7 times 10 to the n. So this is the solution to the recurrence relation. So what we did is, given this, we found out the characteristic equation for the given recurrence relation. We found out the roots and plugged it into the formula. So a solution for the recurrence relation would be given by this whenever the roots are distinct. So in this case 3 and 10 are the distinct roots, therefore this is what you get. If both the roots are the same, then here you additionally get a factor of n. and will not do an example of that kind right now, but this is the crux uh, of the solution. And in order to find the value of alpha 1 alpha 2, we use the initial conditions that were given to us, and by simply solving the equations we found out the values of alpha 1 alpha 2 and plugged it into the equation. Okay, so now we will look at an example of the principle of mathematical induction. So what you are given is, you are given a chocolate which is a bar, which is in the form of a bar. So this is an n cross m bar. So you have some vertical segments and some horizontal segments here, and what you want to do is you want to break it into small pieces. So you want each of the squares to be separated. So essentially you want to break them until all the entire chocolate disintegrates into small squares like that. So now the constraint that you have is that you can only break along the lines that are given. So you can break here, you can break here, and so on, but you cannot break like this or any. So you only are going to break it along the lines and get your chocolate divided into the smaller rectangles. So what the question asks you is, in how many minimum breaks do you need to make in order to disintegrate the chocolate into this small pieces. So what we will do is we will use this idea of induction. Okay, so this is what is called so let me use this principle of mathematical induction, and this question that we're going to do is a bit more complicated than the PMI examples that we saw earlier, because in this case there are two variables that we are inducting on. So normally what you say is, normally the principle says that let's say p of 1 is true, that comprises of your base case, and p of n is true. P of k implies p of k plus 1, then p of n, therefore p of n is true. This is the principle of mathematical induction, but in this case there are two parameters here. So what we will do is we will assume that let's say I break this, let's say I make a break along this column, then I divide the chocolate into two parts. The first part is n cross m minus 1 and the other is 1 cross m minus 1. Okay, so now my task is to optimally solve this and optimally solve this. So how many, sorry, yeah, okay, so how many breaks do I need in order to do this? So I'll write it in this way. So the total number of ways that the breaks that I need for solving it for m cross n bar is the minimum number of breaks that I need for solving an m cross n minus 1 bar. Sorry, okay, I messed up with the m and n again. So p of n comma m is same as p of n comma m minus 1 plus I used one break here to, okay, so I used one break here to break it into this two parts. So I used one here, and then in order to break this into small pieces, what I'm gonna have to do is I'm gonna have to break m, so it's an there are n rows here, so I need m minus 1 breaks in order to in order to disintegrate into small squares, because if it were a row two if it were a 2 row chocolate, then I just need one brick to get them into small pieces. So I need n minus 1 bricks here, and I need one brick here. So okay, plus 1 plus n minus 1. Okay, so what we did is we said that so okay, the claim that I want to, my claim is that the minimum number of breaks that are needed to break m cross n chocolate is equal to mn minus 1. This is the claim that I inductively want to prove. So what would be my base case? My base case would be when I have a single bar of n cross 1. So in this case m is 1, therefore the total number of breaks that I need to do is I'll have to break it across these lines. So that gives me so that gives you n minus 1, and that fits into mn minus 1, which is 1 times n minus 1, which is n minus 1. So this is satisfied. Similarly, the other base case would be when I have a bar like this, which is 1 cross m, and again with the same idea, I'm gonna have to break it across all these lines in order to get it into pieces. So in this case I need m minus 1 breaks, which again fits into the formula, which is 1 into m minus 1, which is m minus 1. So the base case is satisfied. Now we will use our idea that we were describing here of breaking it in the middle, breaking it into one column. So what will that give me? So I want to say that p of n comma m, I want to solve this. So what I'll do is I'll break it into this part, which is m cross n minus 1, by breaking across the column, plus I used one break to get the column, and I want to solve p of m comma 1, and this we know is same as m minus 1. This is from the previous example, and this is something that so this is something that I know is going to be m times n minus 1 minus 1 because of the induction hypothesis, by induction hypothesis. And this turns out to be mn minus m minus 1 plus m, and this is nothing but mn minus 1. So okay, so that is essentially the solution. That so what we did here is that I want to show that the minimum number of breaks needed is equal to this quantity. So for the base case, we considered a single column and a single row chocolate, and we saw the minimal number matches with that. And in order to solve for the bigger one, what we did is we broke this from one column, solved for it optimally, solved for this optimally, and counted the total number. So this is the bigger bar, this is the smaller bar, and this is the one brick that was needed to separate them. This follows from the base case, and this value follows from the induction hypothesis, and if you add them up, the value matches with what we wanted to prove. So therefore by PMI, the minimum number of breaks needed is equal to mn minus 1. And notice that you can also solve the same example. Notice that we in the previous example we recalled this tiling example, and here we are also talking about something similar. Instead of tiles, you have a chocolate, and what you can do is, it indeed the problem has the nature of a recurrence relation. So what you can do is you can formulate it as a recurrence relation, build the initial conditions, and solve it using that. So that's the other question, which I'll probably skip for now, but the answer is very similar to what we did just now. So now what we will do is we will recall the concept of pigeonhole principle. Okay, so this is a very simple yet very powerful technique that we learned in the course. And what does it say? It simply says that if I have n pigeons and I have m holes where m is less than n, so I have some 6 holes, and let's say I have 7 pigeons. Okay, then what it says is if each pigeon goes into a hole, then there has to be at least one hole where there has to be at least one hole which has at least 2 pigeons. So if m is less than n, then there exists a hole with at least 2 pigeons. And while it is a very simple to state and simple to understand principle, the applications it has is humongous. So let's understand this with an example. So let's say there are some n people who attend the party and n is greater than 1. So, and what they do is they shake hands with each other, and assuming they don't shake hand with themselves. So we want to show that there exist 2 people in the party who have shaken hands with the same number of people. So let's see how pigeonhole principle helps us to solve such an interesting statement. So let's say P1, P2 and Pn, these are the n people, and what they're going to do is they're going to shake hands with each other. Okay, so let's write down how many people can P1 shake their hands with. So there are n people, they don't shake their hand with themselves, so they are going to, yeah, so they're going to shake their hands with at most n minus 1 people. And yeah, so they could shake hands with nobody. Yeah, I think, yeah, that's the condition, right? Yeah, so okay, it's possible that they don't shake hands with anybody, in which case the answer would be 0. Or they shake hands with everybody else other than themselves, because this is P1 and then you have P2 and so on up to Pn n minus 1. So there are n minus 1 people, so the maximum number of people that you can shake hand with is this. P2 can also shake hands with 0 or n minus 1 people, and same thing happens with each of them. Okay, now let's say that um, there is somebody who did not shake hands with anybody. So let's say P1 is 0. Okay, then what will happen to the rest of them, P2, P3, P4 and so on up to Pn minus 1? What will happen to them is they will only shake hands amongst themselves. So Pn can only shake n minus 2 other hands. So therefore P1, P2 can only be 0 to n minus 2 and so on, P3 and so on up to Pn minus 1. They can all shake only n minus 2 hands. So now there are n minus 1 people, and there are only there are n people, and there are only n minus 1 values that they can take. Okay, n minus 1 values they can take, then that means that there has to be 2 people who ended up shaking hands with the same number of people. Now if we consider the other case, when there does not exist such a person who did not shake hand with anybody else, then what happens is for everybody the number of handshakes is at least 1. So P1 is between 1 and n minus 1, P2 is between 1 and n minus 1, and so on up to Pn is between 1 and n minus 1. Suppose there does not exist such a Pi who did not shake hand with anybody. Then again there are n people and there are only n minus 1 values that are there. Therefore there must be 2 people who shook hand with the same number of people. And yeah, so that is essentially, yeah, that is one example of the pigeonhole principle that we have, which is again simple to apply, but it can help in proving very complicated statements. And as a last example, what I'll do is I'll recall what is called the chromatic polynomial of a graph. So okay, so what is a chromatic polynomial of a graph? What is the chromatic number of a graph? Chromatic number is simply the number of colors you need to color it properly. So let's say as a simple example, let's say I have this graph and I want to color it properly. So let's say I color the first vertex with yellow. The second vertex I cannot color with yellow because it cannot be same as the color of the adjacent vertex. So what I'll do is I'll color it with green. Then for the third vertex, I can't take yellow because it has an edge like this, and I can't take green because it has an edge like this. So I have to take something other than yellow and green. So let's say I take purple. So yeah, so I need at least 3 colors in this case to color this graph. So the chromatic number of this graph is 3. And what is a chromatic polynomial? Chromatic polynomial is something that tells you if I have lambda many colors at my disposal, then this polynomial tells me the number of proper colorings you can have. Okay, so how do we do that? Let's say I have this graph at my hand, and we saw one very cool trick in the last week, that if you want to solve for this, you can pick up any edge like this, and um, use the fact that the chromatic number for a graph is same as a polynomial for a graph is same as the chromatic polynomial for the graph with deleting that edge, plus the chromatic polynomial for the graph with contracting that edge. So let's see this. So let's say I choose this edge as my example. So what I get is I get 2 graphs. Maybe I'll do it on the new page. If I delete that edge, then I get A, B, C, D, E, F. And if I, this is G minus E, and if I contract that edge, then I get B, A, D, E, F. And let's say I want to solve for yeah, so okay, so let's say I want to solve for this one, for this example now. So what I'll do is I'll again choose an edge and contract and delete. Let's say I choose this edge now. So what is G minus E prime, and what is G contracted with E prime? So by deleting this edge, we are simply deleting this. So what you get is a path like this. So you have B, E, F, D, A. This is the path, and if you contract it, then what you get is B, D, E, F. And now to solve the chromatic polynomial for this, notice that the first vertex I can color in lambda many ways. The second vertex I can color in lambda minus 1 ways because I cannot choose the same node. Then the other one I can choose lambda minus 1, lambda minus 1 and lambda minus 1 and so on. So what you get is lambda times lambda minus 1 whole to the 4. And if you want to do it for this, what we will do is we will apply the trick one more time. So I'll choose this edge this time, E double prime, and get 2 graphs out of it, G minus E double prime and G contracted with E double prime. So this gives B, E, F, D, and the other graph that you get is B, E, F. And yeah, and if you want to solve it for this, now there are lambda min choices for this, lambda minus 1 for this, and so on. So this is lambda times lambda minus 1 cube, and for this is exactly what we had solved earlier. So you have lambda choices for the first one, for the other one you have lambda minus 1 choices, for the third guy you have lambda minus 2 choices, because you can't choose something that was chosen earlier. So for the first part, the polynomials that you end up getting are um, this, this, and this. So that turns out to be lambda times lambda minus 1 to the 4 plus lambda times lambda minus 1 cube plus lambda minus 1 lambda minus 2. And for the other part, you can similarly choose the edges one by one. So you could maybe choose this one and so on, and keep on doing it, and finally add all the chromatic polynomials, and you will end up, and finally adding up all of them will give you the chromatic polynomial for the original graph. So I'll not complete this for now, but I hope that illustrates the trick. And yeah, I think I'll end the lecture there. So what we did today is we looked at chromatic polynomial, we looked at the pigeonhole principle, its application, and solving recurrence relations, formulating them, the idea of principle of mathematical induction, and we saw this formula for solving the recurrence relations, and we saw PIE onto functions, properties, relations, and yeah, basic counting techniques. So I think that is mostly majorly what I wanted to cover for today. And yeah, so I think I'll end the recording with that. So yeah.